Okay, so this is lesson A-3, and this is about the formal definition of something called continuity. And this is page 8. We're actually going to skip this page for now. All right, so that's page 8, where this is where the video notes start, though. And then page 9, there's just some information here about types of discontinuities on a graph, but we're going to skip that for now as well. I'm going to summarize everything that's on that page in this video. So we're going to start off on page 10, and we're also going to use the space on page 11. So I'm going to ask you to, actually, let's go to page 11 right now. And there are, well, first let me tell you about continuity. Okay, we will call this the 3-step continuity test. And it comes from this fact. If the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, which is also equal to f of a, which would be the y value, then f of x is continuous at x equals a. And guys, this sort of double arrow is what's called a biconditional. And sometimes it's translated as if and only if. All right, so it would be all of this stuff, if and only if this is true. And what a biconditional means, or an if and only if, is that it goes both ways. So if this box is true, then this box is true. But it also goes the other way. If we're starting with this box true, then we can conclude that this one is true. All right, so that's how this works here. And in your packet, guys, this is a typo. I think I have two minuses, but that should be a plus right there. Okay. Now that is the definition of continuity. So a function is continuous at a point if this is happening. And if this does not happen, then we say that the function is discontinuous at that value. And we can actually classify different types of discontinuities. So let's write down those classifications, and then we're going to backtrack and do these examples. All right, so this is page 11. And give yourself a moment just to write this down. We're going to have 3 sections. This first section, we're going to explain what it means for a graph to have a jump discontinuity at some x value, x equals a. Jump discontinuity. The second type of classification will be what's called a removable discontinuity at x equals a. And then finally, we're going to have something called an infinite discontinuity at x equals a. Okay. Guys, a jump discontinuity is going to happen, and we could do a biconditional here. So a lot of times you'll have like 2 lines like that and then arrows. And that's, when you're writing, that's usually how they will write a biconditional. All right, so we're going to have a jump discontinuity if and only if we have the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right. And I'll say here, but both limits, both one-sided limits exist. Okay, meaning that they're not infinity. So so it looks like we're hitting the wall at a number from both sides, but the numbers don't match. Okay, that's when you'll have a jump discontinuity. Now, a removable discontinuity at x equals a is going to happen when the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x, but those limits, whatever number you're getting for both of those limits, is not the same as f of a, which would be the y value there. So this is a case where from both sides we're hitting the wall at this, it looks like we're going to hit the wall at the same level, but we don't, but the y value on the wall is not actually at that level. Okay, so the open, if there is a closed circle, it wouldn't be right where it looks like we're going to hit the wall. All right, and then down here, an infinite discontinuity, that is going to happen if and only if we have a vertical asymptote at x equals a, which means that the one-sided limits, at least one of the one-sided limits, is shooting up to positive or negative infinity. Okay, so now that we have that written down, let's go to here. So examples together. So fill in the table below. So we're given here a picture of f of x. And sorry, there's another typo. This should be -8. Those should be -8. Negative. All right. So in this column, we're going to do the 3-step continuity test at the indicated x value. And then we're going to classify any discontinuities as jump, removable, or infinite. Okay. So the 3-step continuity test, we're just going to take this statement here and split it into 3 parts. If we get the same number for all 3 of these, then yes, the graph is continuous at the wall, at the value that we're approaching. All right, so first, we're going to do the limit. Oh, yeah, and let's go, I'm going to put the walls in, and that's totally up to you if you want to. But in all of these cases, the wall is at x equals -8. Okay, so I just put all the walls in like that. Alrighty, so first I'm going to see what number, if any, I get for the left-sided limit, the limit from the left side. So the limit as x approaches -8 from the left of f of x. All right, so let me look. So I'm on the left side, and I'm approaching the wall, and it looks like I'm going to hit the wall at -9. Okay, so that first limit is -9. Now we're going to do the limit from the other side. So the limit as x approaches -8 from the right of f of x. Okay, so now I'm to the right of the wall, and I follow along the graph, and it looks like we're going to, if we keep following this pattern or following this trend, it looks like we're going to hit the wall at -7. Even though we don't end up hitting the wall there because that's a open circle. That's still what the limit is. All right, and then for the third one, we're going to find f of -8. All right, so that's the y value that has the x value -8 on the graph. So you're looking for a closed circle, and it is -9. All right. So guys, if all of these 3 numbers have to match in order for you to say, yes, the graph is continuous at x equals -8, and they don't match, so the answer is no. So not continuous at x equals -8. Okay, so I'll just state our conclusion right there. Now, okay, we'll do this column after we do this column. All right, so moving on, we're going to check the 3 conditions here, and I'm not going to rewrite the notation. Actually, let's rewrite these 3 just for this next one, just to get practice with the notation, and then we won't write the notation every time. All right, so first I need the limit as x approaches -8 from the left. Okay, from the left, it looks like we're going to hit the wall at 6. And then I do the limit as x approaches -8 from the right. Okay, now I'm to the right of the wall, and if I just follow this trend, it looks like I'm gonna hit the wall at 6 again. Okay, so the one-sided limits are matching. And then for the third thing, I need f of -8. So f of -8 is the y value that has an x value of -8. So you're looking for a closed circle, and it's there. It's 10. All right, guys, so these all three don't match. So again, not continuous. All right, now we'll do this one, and I'll stop writing the notation over and over. We could just write the answer. Okay, approaching the wall from the left, it looks like we're going to hit the wall at 0. And then approaching from the right, again, hitting the wall at 0. Now for number 3, this is where we need to look at f of -8. So you're looking for a closed circle. There is no closed circle, guys. So f of -8 is undefined. If there's no closed circle, if there's no graph at the x value, then the graph is undefined there. All right. So, yeah, this is, again, not continuous. We would have had to get 0 for that last one. Okay, 2 more, and then we'll classify them. So this one here, 1, 2, 3. Okay, approaching the wall from the left, we're shooting up to positive infinity. And then approaching the wall from the right, again, positive infinity. So we've got a vertical asymptote at x equals -8. Now for the third one, if you don't see, if the graph does not, if there isn't a point on the graph at a certain x value, then the graph is undefined there, okay? So again, we have f of -8 is undefined, okay? Not continuous. There we go. And guys, by the way, infinity is not a number. So infinity is a type of does not exist. But still, if from each side the graph is shooting up to positive or negative infinity, we go further than saying just the limit doesn't exist. We say it is a type of infinity. All right, now this last one, 1, 2, 3. Let's see what happens here. So first, approaching the wall from the left, -5. Approaching the wall from the right, -5. And then finally, we've got f of -8 that is equal to -5. So all three of these things are the same. So, so the graph is continuous at x equals -8. Okay, so it was only that last one. Now here, classify any discontinuities as jump, removable, or infinite. All right, so this last one was not discontinuous. It was totally continuous, so I'll cross that out. Okay. So this first one, guys, is actually, it's a jump discontinuity because the one-sided limits are not equal, but they each exist, but they're not equal. All right, so this first one is a jump discontinuity. Guys, the second two are both removable discontinuities. The reason is that the limit from the left is equal to the limit from the right, but those are not equal to the y value on the wall. So either there is no y value on the wall or it's not at the same level as the limit. All right, so yeah, so both of these next two are removable. All right, guys, and then an infinite discontinuity is going to be when you have a vertical asymptote. And that's going to happen when a limit is equal to infinity. When you're approaching a wall, as x approaches a wall, the y's shoot up to infinity. So this is infinite. Okay, there you go.